All right, this will be our final lecture. So I would like to spend most of the lecture going over some examples um, from the second part of the course, because for the most part, the first part of the course remains relatively unchanged. So things like our basic probability rules, all of our distributions, right? We should understand all of that. And the best way, I think, to understand all of that would be to go back through all of the previous exams that I've sent you. Of course, the exams that we did in the course, as well as some of the practice final exams that I sent you. Right? Going over all of that stuff should help give you plenty of practice on this material. Okay. One of the next things that we went over was some confidence intervals, so I just want to briefly review these. I should have sent this to you at some point. So for a confidence interval for a one sample mean, right, we just use t.test and we simply put our data set. Okay, and that's pretty much it. For two samples, right, we have three cases. We have to decide whether they are independent or dependent. Of course, if they're dependent, then we are done and we just have to put, we have to add paired is equal to true. However, for the t.test function, you have to put the first sample, comma, the second sample, okay? So that could look like something like this, or if it's a data set that you have attached, then you might be able to use a column label for these two things instead of something like this, data bracket comma 1 bracket, data bracket comma 2 bracket, okay? So it could just look like a data, a column label if you have attached your data set. But in either case, if you've determined that the samples are dependent or matched pairs, you just simply have to add paired is equal to true. If you determine that they are independent samples, you have to determine whether the variance is equal or not. If the variance is equal, then we simply have to put comma var dot equal true. Okay, and how might we determine if the variances are equal? Well, you could either do a side-by-side box plot, or you could simply calculate the sample variance of each group, right? Kind of, you could put, again, this could look like this, or it could look like just a column label, right? If you simply put var and put this in parentheses, right, it gives you the variance, and do the same thing for this. It spits out the variance, and if those two variances are extremely close, then you might be able to assume that they're equal. If they're not extremely close, then we should not assume that they're equal, and we simply put var.equal equal false. So of course, what we're looking for in the two sample case is we're looking for to see if the confidence interval contains 0. If it contains 0, then we do not have evidence that one of the means is bigger for one of the two groups. If it's completely positive, then we have evidence that the first group has a higher mean. If it's completely negative, we have evidence that the second group has a higher mean. Okay, and the only other confidence interval that we went over was for proportions, and we simply used a prop.test function, and the two arguments are simply the number of successes followed by the number of trials, and you do have to make sure you put everything in the right order with pretty much all of these. Okay, and with any of these functions, if you need something other than a 95% confidence interval, you simply have to add the argument comp.level and then put equal to whatever confidence level you desire. Okay, so I think we've had enough practice with these that hopefully these are fairly standard for you now, and you have a very good understanding of how to implement these. Okay. All right. So the next thing I want to look at, just to again kind of get a feel of the format. The format is basically going to be like the second test that we had, which was online. Okay. So um, this was a Weibull question, but this could also be like a gamma distribution question, right? And so you could be given some function, and well, in this case, a question, but you might have to calculate the CDF or some probability based on this function, right? And so one quick thing, Weibull distribution, right? We need to use U substitution, and gamma distribution, we need to use integration by parts, right? So you could be given a gamma or Weibull distribution or just some random distribution that's not named, and you might have to calculate its CDF or its survival function, its hazard function, or some probability, right? Some conditional probability like this, okay? Okay, so this is a good example of something that I could put on the final exam, a question like this, and so we'll go ahead and do another practice example of a question like this, one where we're trying to model data, okay? So I have a example data set here, which I've just named data, okay, which I'll have sent to you along with concrete data. And so let's go ahead and read that into R. The first thing, well, one thing I'll show you that you might want to do from time to time is if you put ls and then open close parentheses, well, you're not going to have this much stuff, but things that you've saved in the past, things that you've basically defined, you might have a bunch of stuff here, and sometimes that could, if you try to name something the same as one of these things and you try to attach something, it could cause a problem. It's unlikely probably to cause a problem for you, but just in case, if you want to kind of clear all of this stuff, and for example, what is all this stuff? I'll just put like y.true, right? That basically means this is saved, this is something. So like y.true, this is a vector of 5,000 zeros and ones, okay? And sometimes you might want to remove all of this garbage from being saved kind of in the background of R, and if you put rm for remove, parenthesis list equal ls, parenthesis close parenthesis. Now I don't have anything in the background, right? So like y.true, right? There's nothing. Okay, that way sometimes if you're trying to attach a data set, but maybe one of your previous data sets is the same name as one of your column labels or something, it could cause a problem. But anyway, this may or may not be useful for you, but I just want to go ahead and go over it. Okay, so we want to first, again, we're trying to do a problem similar to this. We have a data set, and we want to model the data set, okay? And in this case, I'll give you three choices. Actually, these three choices are good, okay? Oftentimes, I might also give you the fourth choice of the gamma distribution, okay? But the way we do that's pretty much the same. But anyway, I'll stick with a similar like this: exponential, normal, Weibull, okay? Let's try to use those to model this data. So of course, Weibull analysis code gives me my line that I can use to read the data in. And the data is in fact called data, although I could have to change that. Okay, change my username. And so this time I have 1,000 observations. Okay, and so we want to choose those three different models to try to model this data. So our Weibull analysis code need to do this. Okay. Our shape and scale parameter for the Weibull. Oops. I forgot I'm not supposed to give you more than 1,000 observations. Okay. We're going to change something. All right, no, we'll keep it like this. Okay, so I've got 1,000 observations. Okay, so what I need to do is I need to change this to account for the fact that there's 1,000 observations. Okay, so I need to change it to, oops, need to change it to this. Okay, so basically you just need to think about, if I have 1,000 observations, then I want to take 1,000 steps. So each step should be size 1/1000th, right? Okay, so that's basically the gist of this. I need each step to be size 1/1000th, so the last step should be, of course, one less than that from 1. Yep. Okay, so let's look at this. Okay, so we can see it looks really nice, everything to here, and a little bit here, right? But not much. Okay, that looks relatively nice. Okay, relatively nice. Remember, there's 1,000 observations here. So, almost all the observations are here where it gets really thick. And it goes a little bit away right here, but not much. Okay, so overall looks pretty good. And histogram, just got to make sure we change our values. All right. And again, this looks pretty good. Okay, one thing, if you notice the line here, basically the straight up and down line, that's um, that's shouldn't be there. It's just kind of annoying how R puts that there. So basically, we just have our histogram, and then we have this curve here. Okay. You can basically just think about this as a line at 0. It really shouldn't be there, though. Okay, so we can see that our curve fits the histogram very nicely, right? The histogram appears to be very right skewed. It's got a really big amount of probability here, and then less, less, less. So it's very just a right skewed, okay, distribution. And so that's what our curve is looking like, is very right skewed. So that Weeble seemed to fit very nicely. But let's go on. The next distribution to try would be the normal. Get our maximum likelihood estimates, stick them in here. Make sure to put our comma if you do it like I just did. And also make sure to change the distribution to normal, which is just norm. Okay, so hopefully we can tell that this is absolutely horrible, right? Just horrible. Now, from this, there's really even no need to look at the histogram, right? We should be able to tell that this is a normal model, is just not appropriate in the slightest to model this data. Okay, but just to see how horrible this looks like on the histogram, let's go ahead and look at it. And I hope you're following along with me as we're doing this, right? You have the data set, you can do this on your own, okay? So the reason this looks so horrible, right, is because here's our normal distribution, right? About 40% of the probability. Apparently, in this data set, there are no negative values. Okay, I didn't really say what this could have been. This could have been a time variable, but in either case, there appears to be no negative values in the histogram, right, in the actual observed data. And this normal distribution, right, just thinking about that, that's probably about 40% of the probability that's being chopped off, right? So this just doesn't make any sense at all to model this data. Okay, so clearly the normal distribution is not appropriate. Now the Weeble distribution looked quite nice, but we have one more exponential. Okay, and we need our maximum likelihood estimates, right, which is just going to be 1, right, only one parameter in the exponential distribution. QExp, right? Okay. Now I didn't save. I probably should have, and I'll go ahead and show you how you can, or remind you how you can. To me, just at first glance, this looks almost exactly like the Weibull distribution. Maybe I should go ahead and create the Weibull one because I can't remember any difference between this and the other. Okay, so one thing we can do is put Windows. Okay, and I'll go ahead and go back to my my Weibull distribution because Weibull. I can't really tell much of a difference there. Okay. So normally we hopefully you wouldn't have to go back and do this step if you had just put Windows the first time. After each plot that you made, if you put Windows, you can basically save all of them. Okay. And also if you're going to do this though, it might actually be helpful to put labels. Okay. And so here are my two graphs. They look extremely similar. They basically look the same to me. I can't really tell much of a difference. Okay, these look basically the same. Okay. So well, I've already got my Weibull here, so since we know it's probably going to look pretty close, I'm going to go ahead and remake. Here's something I'll do, and maybe something to be helpful in a case like this. dWeibull, so going back to the Weibull distribution, and what I'll put here is I'll put main equal Weibull. Okay, so in my hist function right here, I'll put main is equal to Weibull in parentheses. And I could have put the same arguments at the end here. Again, separated by a comma. I could have put the same here when I wanted to distinguish that it was a Weibull QQ plot. Okay, so that's what I'm going to do. I'm going to remake. So this is my Weibull histogram. Okay, we already saw that one. So now what I'm going to do is I'm going to Windows parentheses to create a second window. And now let's get the exponential one. Okay, change that. Have to remember to change this or we're going to get the wrong answer. And I'll change my title to exponential. And let's go ahead and graph that one. Okay, now we can kind of compare side by side. Okay. Again, these look extremely similar. They both appear to fit the data very nicely. Okay. So with that being said, it appears to me that both the exponential Weibull distribution have almost identical histograms and almost identical QQ plots. They both seem to model the data equally well. So what then would you choose? Okay, we have Weibull, normal, exponential, or at least two of the models are equally good. So I don't know that I would put this on the exam because it would almost be like a trick question. Okay, so technically the two models model the data equally well. But something I have mentioned in the past, the exponential has a leg up on the Weibull in this case. Why? Well, here's our Weibull distribution. It has two parameters, a shape parameter and a scale parameter. The exponential distribution has a single parameter. Okay, that in essence makes it a simpler model. Okay, because instead of requiring two parameters, in order to properly model the data. I only require a single parameter to model this data. So technically it's a simpler model, right? Because instead of having to report that it's a Weibull distribution with shape parameter that 1 and scale parameter 2, right? You just simply report it's an exponential distribution with rate parameter 0.5. And of course, it's also easier to calculate things like the expected value and variance for this exponential than it is for the Weibull, right? The formulas for calculating the variance and the expected value are much more complicated for the Weibull, right? For the exponential, it's simply 1 over lambda is the mean, 1 over lambda, or 1 over lambda squared is the variance, right? So we know immediately that this exponential, I'll just round this to 0.5, right, has a mean of 2, right, on average, and a variance of 4, right? And so it's much easier to relay the information for an exponential 0.5 than a Weibull 1, 2 distribution. So just on that basis alone, the fact that the exponential is a simpler model, I would choose the exponential distribution because both models are equally good in terms of how they're actually modeling the data, but the exponential is a simpler model. And the same thing kind of goes in regression as well. If two models are equally good, but one is a simpler model, right, has like less variables in it, then that's the one that normally you would want to choose. Okay? But as I said, kind of if I were to put this, it's almost like a trick question. So I probably won't put one like that. Um, it would be more, for this to be the correct answer, it would probably be like the Weibull and the normal being equally good. Okay, something like that, because they both have 2 parameters. So if they both fit equally well, then B could be the right choice. Okay, so in general, I'm going to test you on what you know, but not try to be tricky about it. Okay, we saw this one on the last exam. It was a proportion question. So, right, all we had to do is basically just put prop.test, like 535 and 1,000, and change the confidence level to 98% and done, pretty much. Okay, so these confidence interval questions, hopefully you should just be able to fly through them. Of course, take your time, make sure you don't make any mistakes, but they shouldn't take you much time. Okay, another confidence interval question, it looks like. Right, this was one where you did have to think a little bit about things, but it was a 2-sample confidence interval question. Okay. This was an ANOVA question, and actually I'll go ahead and do this right now just so we can see. Okay, so we're comparing the average lifetimes of 3 types of batteries, and just to give us another ANOVA example, you can still, I think, I'll just send it to you in case it's not visible anymore. Okay, exam 2 battery. Okay. Exam 2 battery. Okay, and I'll call it BAT. Call my data set. Again, you can call it whatever you want. Let's look at it. Okay, so we've got our lifetimes and we've got our battery labels. And I think we're gonna, do we have labels? Yeah, lifetime battery. So I can attach that, so I can use my labels. And it's probably gonna be the same thing. And if I give you an ANOVA question, it's going to be like this. So I'm probably just going to recommend that you put as dot factor here. Yeah, because I'm sure it's going to give me the same thing. Yeah, okay. So since this is your code, and if I give you an ANOVA question, I'm going to put the labels as numerical because it's much easier for me to do so, okay? So if you've got a regular label, like a word here or something, right, like we did in that flower example, right, where we had the flowers, we had actual words here, then you don't need to change this. But for the exam, I'm certainly going to give you, if I give you an ANOVA question, I'm going to have labels as ones, so you might as well go ahead and include as dot factor and then put parentheses around the variable, okay? Because that is necessary to treat this as 3 categories and not just a bunch of numbers, okay? And as I've said before, one double check is this first number here in the table should be one less than the number of groups that you have. And of course we have 3 types of batteries, right? 3 groups of batteries, so I should see the number 2 here. I saw the number 1 here, right, in the previously, and we could tell immediately that it was wrong. Okay, so my p-value is basically 0. So because the p-value is less than 0.05, unless I gave a different significance level, right? 0.05 significance level, because the p-value is less than 0.05, we reject the null hypothesis that the average lifetimes are the same, and thus we have evidence that the average lifetimes are different. Okay? So this one is incorrect because we're failing to reject the null hypothesis, right? When the p-value is smaller than the significance level, we reject the null hypothesis, not fail to reject. Okay, this is also fail to reject, but to see why this one is wrong, it says reject the null hypothesis and thus do not have evidence that they're different. Okay, that's wrong because we do have evidence. Whenever we reject the null hypothesis, we have evidence of a difference. Okay? And so this is a follow-up question based on the hypothesis test. Do we need to do Tukey pairwise comparison? Right, we just found that the average lifetimes are different. Thus, we do want to do the Tukey comparison to determine where these differences are. Okay, so yes, we need to. And so Tukey. So species as dot factor battery, sepal width, lifetime. Okay. All right. And so from here, this confidence interval is completely positive. Again, you can ignore this column and this column. This confidence interval is completely positive. So 2 has a bigger mean, group 2, right, battery 2. This one's completely positive, group 3 has a higher mean. This one's completely positive, so group 3 has a higher mean. Okay, so group 3 has a higher mean than group 1 and group 2, right? So immediately it has the biggest mean. And then from right here, group 2 has a higher mean than 1, thus group 2 must have the second highest mean, and group 1 must have the smallest mean, the least average lifetime. Okay? And again, if we have one of these confidence intervals including a negative sign, then we can, from going from negative to positive, then we're not going to be able to order all of the means, okay? But we should be able to at least order one of the means. If we detect a difference, at least one of these confidence intervals won't include 0, but it's possible for 1 or 2 of them to include 0, it just depending on the case. Right? And again, of course, if these were just simply, if this was negative and negative, then that would just be indicating that the second group had the higher mean, okay? All right, so that's basically that. Okay, concrete. Here's a regression example. So let's read in our data. It's just called concrete. Let's call it con. Let's look at it. Looks like we have 4 variables: integrity, concrete, water, temperature, and we have 100 observations. Okay, so what these are, this is the integrity, basically an integrity score of some concrete foundation, basically, right? The higher, the stronger it is. Okay, this is the thickness of the concrete, okay, in some units. This is water. A 1 indicates that water was added to the concrete. A 0 indicates that water was not added to the concrete. And temperature is just simply the ambient temperature where this concrete foundation is laid. Okay? So, one of the things that we might want to do is simply start with a linear regression model where we just have the lower order terms. That is, we have basically y is equal to beta naught plus beta 1 times x1 plus beta 2 times x2 plus beta 3 times x3. Okay, so start with a simple, well, start with a linear regression model with just the lower order terms. Okay. So ANOVA and regression. Okay, so the first thing, right, we want to use these labels so we can attach con, or whatever you call your data set. And so I'll skip the scatter plot for now. We could do scatter plots of integrity against each of the variables if we wanted. But what I will do is linear model y, which is integrity, against, is it called concrete? It is called concrete. So x1 is concrete, plus x2 is water, plus x3 is temperature. Okay? So this is my, right here, this is my fitted regression model here. So we basically have y hat, which are the estimated integrity scores for our concrete, is equal to the intercept, negative 3.4. Right here, I'll just be rounding to make it look cleaner. Negative 3.4 plus 1.4 times the width or the depth of the concrete plus 16.2 times water. Again, water is either a 1 or 0, right? It's a 1 if water was added. It's a 0 if water wasn't added. And then again, another plus, right? It turns into a minus if the parameter, the estimated parameter is negative, but they're all positive in this case. Plus 0.3 times temperature. Okay, so that's our fitted regression model. And so anytime we want to predict the integrity, right, we just take the intercept and then plug in concrete, plug in water, plug in temperature, right, whatever values we might have for a certain concrete foundation, and then we get a estimated integrity score for such a concrete foundation. Okay. All right, so is this any good, right? Summary, reg.model. Well, one thing we can look at, R squared, right? Our model with the 3 variables, concrete, water, and temperature, account for about 82.5% of the variability in the integrity score of a concrete foundation. Okay, so that's fairly good. Okay, let's look at our p-values. Okay, very small, indicating concrete is significant, right? Very small, indicating water significant, and I haven't specified anything else, so unless I do, comparing this to 0.05, this is less than 0.05, right? So we still reject that beta 3 is equal to 0, right? So again, temperature seems significant, right? If the parameter is 0, that indicates that that variable isn't significant. So this is still less than 0.05, so maybe not as significant as these two necessarily, but still less than 0.05, indicating that temperature is needed. So all terms appear needed in the model. It accounts for a decent amount of the variability. Okay, but there's certainly one more thing that we have not done, and that is check the assumptions. Okay, so to do that, right, we do plot reg.model, and it looks like it's going to be on this because I have two. Remember, you have to click. Okay, so this is our residual plot. So it should be obvious from this. Remember, not all assumptions being violated are completely obvious. Sometimes they are. This should be obvious that this model is horrible. Okay, it appears that we are not modeling this data correctly, right? We want this red line to be flat at 0, and we want a random cloud of points. We have a nice, right, quadratic relationship here. We have a nice curvilinear relationship. Thus, we are not modeling things correctly. So I've mentioned before, this could indicate that a quadratic component, like a squared component, is needed. Okay, but it can also indicate something else. It could also indicate that an interaction term is needed. Okay, and so you might just have to try the things for yourself, right? You could try adding concrete squared, water squared, and temperature squared into the model and seeing if that fixed this. Okay, I don't think it will though, because the reason it looks like this is because there is a very distinct interaction. Okay, so thinking about our two variables, water and concrete. Okay, so right, the concrete is the thickness of the concrete, and water is whether water is added to the concrete. Of course, water should be added to the concrete, right? We don't just pour a bunch of dry concrete in a foundation and call it a day, right? You have to mix it. So thinking about that, does it matter how thick the concrete foundation is if we don't add water? Well, probably not, right? If it's 1 foot thick or 10 foot thick, it probably doesn't matter a whole lot if it's just a bunch of powder, right? But whether it's 1 foot thick or 10 foot thick probably matters a whole lot if they're both proper foundations with water added. Okay, so basically there's an interaction, right? How thick the concrete should matter a lot, but only if it's an appropriate concrete foundation with water actually have been added, right? So we can see up here, right, a bunch of concrete foundations, right? We have a bunch of hobos working on them, and they didn't add water to the concrete, okay? So it doesn't really matter how thick this concrete is, right? It still has a crappy integrity score because we didn't add water, right? So the thickness of the concrete matters a lot, but only if water is added. So that logical wording right there implies that there is an interaction between concrete and water, right? The thickness of the water matters, but dependent on whether water is added. Okay, that's basically the definition of an interaction. Let's look at the normal QQ plot. We can also see that the residuals do not appear normally distributed. Okay, so basically we've just got a horrible model here. So that's one reason understanding the assumptions are very important. Okay, because as I said, we could have just fit this model, seen that we have a reasonable R squared, that the terms in the model are significant, and just reported, okay, here is our model. Okay, and that would just make you, right, not very good. Okay, so that would just be a horrible thing to just check these and say this model is good. Okay, because as we saw from these two plots, this model is horrible. Okay, there's the assumptions are violated. We're not modeling the regression function properly. Okay, so as I've said, we could think about adding a bunch of course you have to predefine them, like con2, well, I'll go ahead and put it like con2 is equal to concrete squared, and likewise water or watt2 is equal to water squared, and temp2 is equal to temperature squared, and then you could put integrity is equal to concrete plus water plus temperature plus con2 plus watt2 plus temp2. Okay, That's how you could add squared terms, okay? And you could see, and a lot of times that is necessary, right? That fixes it because there's a, well, we could also look too, though. Here, let's go ahead and do that. Go away. Let's look at each of the individual scatter plots, okay? Because if there's a curved relationship, that's when it kind of gives you an inkling that there is a quadratic term needed. So let's look at x is concrete. Let's look at x1 versus y. Okay. Now, here's x1 versus y. This should look very strange to you, right? Half of the points have this nice linear relationship. Half of the points are flat. Okay. What is this? Okay. This is what is indicating that an interaction is needed. Okay. This is basically the points where water is added, right? When water is added, then it is natural that the thicker the concrete foundation, the more integrity the foundation has. But for all of these points, right, water wasn't added, so it doesn't matter how thick the concrete was, right? The integrity is about the same because it's a bunch of useless rubble, right? A bunch of useless powder, okay? So some sort of crazy pattern like this might be an indicator to you that an interaction is needed, right? For the squared term, right, if it looked like maybe a squared, concrete squared might be needed, we might see a squared, curved pattern, okay? But again, this is a very strange thing, something you probably usually wouldn't see, but this is like a very, this is a kind of a clear indicator that something is going on, right, with concrete integrity. Something else is going on, and what that something else is in this case is an interaction between concrete and water. Okay, nonetheless, let's look at water just for fun. Okay, now this isn't crazy. The water only has two values. Okay, okay. Still not going to look crazy, but we need to make the right plot. Water and integrity. Okay, as I said, two values. Water, this is when water is not added. This is when water is added. Okay, and so we can see when water is not added, we have all these low integrities, and when water is added, we have a range of integrities that are much higher. Okay, so this makes sense, right? That water being necessary, so this kind of indicates, right, water clearly is necessary in predicting the integrity, because all of these integrities are much higher when water is added. Okay, and the last one is temperature. Temperature. Okay. Um, to me, not a whole lot going on here. Okay. Looks pretty random. Right, as temperature goes up, is integrity going up? Not that I can really tell so much. Okay. Not really sure. It doesn't look like temperature is really doing a whole lot. But anyway, from those three scatter plots, right, there was no curved relationship, right? Kind of giving us evidence that, okay, we need to add that curved relationship to account for that curve that we saw in the residual plot to fix it. What we did see is when we plotted concrete against integrity, we saw something very strange. Okay, and as I mentioned, it's because concrete and water interact, right? I mean, obviously, you're not going to have a real data set where you had a bunch of morons not add water to the concrete, but just think about something similar, right? There's clearly water is important with concrete, and they interact together to make a proper foundation with a higher integrity. Okay, so let's go back up. I'll call this reg.model2, and what we'll do is to try to account for that interaction, we're going to add concrete times water. I don't think we have to predefine this like we do the squared terms, okay? But we're about to find out. Okay. So now this regression model, we have the integrity score is equal to 10 minus 0.1 times concrete minus 0.6 times water plus 0.2 times temperature plus 3 times concrete times temperature, right? Interaction, you just multiply them together. Okay, so if we know the thickness, if we know whether water is added or not, and we know the temperature, we just plug them in and we get our predicted integrity score. Okay, let's look at the summary. Look whether these terms actually appear needed. Okay. So the interaction, kind of looking here, right? This is the term that we didn't have before. We had all these. Highly significant. Okay. Highly significant. So also, well, just looking here, we're now accounting for 99% of the variability in integrity. Okay, that is a huge jump from the 82. So this alone is giving you indication that we clearly needed this interaction. And also the model is stating that this interaction is needed. It's also stating that temperature is needed. Okay. To be honest, this kind of surprises me just looking at the scatter plot anyway. It didn't look like temperature was that related. So maybe there's something else going on here that I'm not seeing, right? But this temperature appears highly needed. Now look at concrete and water. These do not appear needed, right? These are both greater than 0.05, which means that looks like maybe beta 1 and beta 2 are equal to 0, which means we can kick them out. They might be equal to 0. Now, of course, I've said before that you can never kick more than one thing out of the model at the same time without doing a partial F test or a overall F test if you're testing whether everything can be kicked out. However, there is no need to do a partial F test in this case. These are our three lower order terms, right? Just basic terms. This is what's called a higher order term. As I've said before, when you have like concrete squared or concrete cubed or natural log of concrete or something like an interaction concrete times water, any of these higher order terms, if any higher order term is necessary, right, this higher order term is necessary, you would never kick out lower order terms even if they do not appear significant. So because the interaction between water and concrete is necessary, even if it doesn't appear that the lower order concrete alone or water alone is necessary, you would simply still keep it in the model. Likewise, if we had something like concrete squared here and it was significant, you would still keep just the basic concrete term in the model, basically the linear concrete in the model, even if it didn't appear significant. Okay, so if a higher order term like a squared, cubic, etc., or interaction is necessary, you keep all lower order terms in the model regardless of whether they are necessary or not. Okay, now pretend that this was a big p-value for a second, like flip those p-values. We could kick temperature out of the model because it doesn't have a higher order term, right? This higher order term has nothing to do with temperature. So if temperature had a big p-value, we could still kick it out of the model. But in this case, it doesn't, so everything should be kept in the model. Okay? So p-values, it looks like the interaction was necessary. It looks like it is a much better model, 99% of the variability versus 82% or whatever, right? But we still have to check the assumptions, okay? It could still be possible that the assumptions are violated, okay? And sometimes fixing one assumption makes one assumption worse, okay? But in either case, let's look at the assumptions. Plot reg.model 2. Again, remember you got to click. Okay, remember we had, I forget which shape it was, but we had a clear curved horrible relationship in this residual plot before. This looks much better, okay? Now, it's not perfectly at 0, but it's pretty close, okay? And again, the fact that there are a bunch of points right here versus here is not a bad thing. It's just because we have a bunch of integrity scores around 20. That's not a bad thing, okay? So what we're trying to look at is the overall kind of spread on the Y, right? It looks like for integrity scores around 20 versus these big integrity scores, they have roughly a similar spread, right? As well as being both positive and negative, okay? So overall, this looks good. I'm also not seeing some sort of a megaphone shape, right? So this is indicating that the expected value, right, although not perfect, it appears relatively close to 0. There does not appear a correlation, right, like some just nonstop increasing or decreasing pattern. The regression function appears to fit, right? We don't have that big curve. And it looks like the variance is fairly similar. The spread on the y-axis is pretty similar for all of the x-axis values. So we appear to have constant error variance. So much, much better than the previous model. Let's look at our normality plot. If you recall, this was also horrible. And although this might not happen all the time, it appears that adding our interaction term not only fixed our residual plot, but it actually fixed our normality plot too. Okay, this looks very good, right? Of course, a little bit here, but that's that's nothing really. So this looks very good. So overall, looks to be a great model. Okay, all of our assumptions are satisfied. We've checked about our terms being included in the model. We account for 99% of the variability and integrity, so all that combined leads us to say that this is an extremely good model. Okay, very, very good model. Okay, so if we want to predict the integrity score for a certain foundation, right, I could say, okay, the concrete foundation is 5 inches thick, water was added, and the temperature is 50 degrees. If that's the case, right, you would just put 5, however thick it was, plug it in here and here, right? Plug in, if water was added, plug in a 1. Of course, I would specifically tell you 1 means water's added, 0 means it's not. And then 50 degrees or whatever, you plug 50 in here. Oh, sorry, this was water. Okay, I didn't notice that when I was saying it. The interaction is between concrete and water, right? Concrete and water, not concrete and temperature. Okay, so concrete times water. Okay, so plug in the values, and whatever number you get, right, make sure you include the interaction, is the integrity, the estimated integrity score of the foundation. Okay, we haven't done these in a while, so let's go ahead and do this. Okay, an estimate of the error variance. Reg.model2. Okay, ANOVA, reg.model2. The residual mean square, 1. Well, there's our estimate for the variance. So the variance estimate is 1. That is the MSE, error mean square, or residual mean square. Let's do 90% confidence intervals maybe for these parameters. Okay, right? We're 90% confident. oops, reg.model2, right? We should have an interaction, right? We're 90% confident that beta 1 is between here and here, beta 2 is here and here, beta 3, and beta 4. Okay. And of course, always whenever we're interpreting the coefficients or interpreting confidence intervals, you want to put it in the context of the problem. Can we interpret these? We cannot interpret these coefficients. Well, the only coefficient here that has a nice interpretation is temperature. Okay, whenever we increase temperature by 1 degree, the integrity score of the foundation increases between 0.16 and 0.28. Nice interpretation. We no longer have a nice interpretation of when the concrete increases by 1, the integrity, of course, this is negative, which looks strange, but that's because there's an interaction. The integrity decreases by negative 0.2 to negative 0.01. We also do not have an interpretation for water, okay? Because I can't just increase concrete by 1, okay? The effect that concrete has